Hi everybody, Mrs. Pesic here,
And Miss Bella here.
and we are looking at section 7.5, compound events. The objectives in this section are to find the probability of mutually exclusive events and to find the probability of inclusive events. And your vocabulary: simple event, compound event, mutually exclusive event, and inclusive events.
So to start off, we're going to say that a simple event is an event that describes a single outcome. A compound event is an event made up of two or more simple events. Mutually exclusive events are events that cannot both occur in the same trial of an experiment. So for example, rolling a 1 and rolling a 2 on the same roll of a number cube are mutually exclusive events. So again, event A and event B means that they would have no overlap. They are both independent of one another. So whenever we have mutually exclusive events, the probability of two mutually exclusive events, A or B, occurring is the sum of their individual probabilities. So for two mutually exclusive events, A and B, we're going to use this symbol right here to represent A or B. So we'll add the probability of A to the probability of B. So it is a sum there. So our example here, when a number cube is rolled, what is the probability of rolling less than a 3? Well, that's the probability of getting a 1 or a 2. So the probability of getting 1 is a 1 out of 6. Probability of rolling a 2 is also a 1 out of 6. So I'll add those together to get 2/6, which reduces to 1/3. So again, the symbol we'll use when we talk about exclusive events or is the symbol right here for union, which looks like a U, and again, that means or. So we would add the two probabilities together there.
All right, so let's take a look at an example. A group of students is donating blood during a blood drive. A student has a 9/20 probability of having type O blood and a 2/5 probability of having type A blood. Explain why the events type O and type A blood are mutually exclusive. Well, they're going to be mutually exclusive because it's impossible for you to have type O blood and type A blood at the same time. Everybody's just got one blood type. All right, and now what is the probability that a student has type O or type A blood? These are mutually exclusive, so we're just going to add the two probabilities together. So probability that you have type O or type A is going to be 9/20 plus 2/5, which gives us 9/20 plus 8/20, which is going to give us 17/20. So the probability that you have type O or type A blood is 17/20. And there's all the hard work that I could have just done.
All right, so that's going to take you to your first must do. Each student cast one vote for senior class president. Of the students, 25% voted for Hunt, 20% for Klein, and 55% for Villa. A student from the senior class has been selected at random. So explain why the events voted for each of those three candidates there. Why would that be mutually exclusive? And then what is the probability that a student voted for Klein or Villa? So again, remember we're going to do a summation here as long as we can say for sure that they are mutually exclusive. Now, if they are not exclusive, we're going to call them inclusive. So inclusive events are events that have one or more outcomes in common. So when you roll a number cube, the outcomes rolling an even number and rolling a prime number are not mutually exclusive. Again, exclusive would mean that they have, no overlap. They're independent of one another. They are not affected, or have nothing in common, I guess. So the number 2 is both prime and even. So again, rolling an even number and rolling a prime number are going to be inclusive. So we have a Venn diagram here, which is usually the best way to kind of see what's happening. Here in red, rolling a die on my number cube, all of my even numbers I could get are 2, 4, and 6. In blue, the prime numbers I could get are 1, 3, and 5, or 2, 3, and 5, excuse me. Remember, 1 is neither even, it's not even, 1 is also not prime, so we see it nowhere on our Venn diagram here. In the middle, we have 2, which is both even and prime, so that's going to be in the intersection. So our symbol right here is going to mean and that is the intersection symbol, so that's going to be when we have inclusive events.
So 2 is the only number that is in the intersection of even numbers and prime numbers.
Correct. Now, when we kind of look down here again, how do I roll an even number? I had 2, 4, 6. How do I roll a prime number? Well, that was 2, 3, and 5. So the outcome 2 is counted twice when the outcomes are added. So I had 3 outcomes in the red circle or oval, 3 in the blue. So I would think that there are 6 possible outcomes. Again, I would take how many in the blue and how many in the red and add those together. However, the actual number of ways to roll an even number or a prime number is 3 plus 3 minus 1, or 5 ways. So the concept of subtracting the outcomes that are counted twice, so anything that falls in that middle part, that intersection, we're going to have to subtract those from my total outcomes. So that's going to give us this formula on the next page that would describe this situation.
So we were subtracting 1 because there was one item in the overlap. Okay. All right, so inclusive events. Let's talk about the words that we've just been using. So the probability of two inclusive events, A or B, occurring is the sum of their individual probabilities minus the probability of both occurring. In algebra, our symbols would be the probability of A and B occurring would be probability of A plus probability of B minus the overlap, the probability of both of them occurring. Isn't this supposed to be the word? Is it? For for A or B happening, it's going to be pause. Okay, so we left off right here. So for two inclusive events, A and B, and I don't want to have this word here because this word is supposed to be right here. So for two events, A and B, the probability of A union B, where the union means or, all right, so the probability that A happens or B happens is going to be the probability that A happens plus the probability that B happens, and we have to subtract off any overlap when A and B happen at the same time. So for example, when you roll a number cube, the probability that you get an even or a prime number is going to be the probability that you get an even number plus the probability you get a prime minus the probability that you get an even and a prime. So that was 3/6 plus 3/6 minus 1/6, and that gives us 5/6. And that goes along with the example we were just looking at.
So our example here to try this on our own, find the probability on a number cube of rolling a 4 or an even number. So again, we're looking for rolling a 4 or an even number. So we are looking for the probability, we'll just kind of write this out here. So rolling a 4 or, so that would be that symbol, a union here, or even number. Well, in order to do this, what we're going to have to do is we're going to have to take the probability of getting a 4 plus the probability of getting an even number, and I'll subtract the probability of getting a 4 and, so that's my intersection, and an even. So how many times that would occur? So the probability of rolling a 4 on a number cube is 1 out of 6. The probability of rolling an even, well, that's 2, 4, 6. That's 3 out of 6. And how many times can you roll a 4 and an even number? Well, that's only going to be when you have a 4, because that's even, so minus 1/6. So 1/6 plus 3/6 minus 1/6 is going to give us a grand total of a probability of 3/6, which I could reduce to 1/2. So my probability of rolling a 4 or an even number is going to be 1/2.
Okay, that brings up your next notes must do. Find the probability of rolling an odd number or a number greater than 2 with one roll of a number cube. So remember, you want the probability of an odd or a number greater than 2. So that's going to be the probability of the odd plus probability of getting a number greater than or greater than 2 minus the probability that both occur. Okay, let's take a look at example 3. A card is drawn from a deck of 52. You know the standard deck of cards. Find the probability of each. So what's the probability of drawing a red card, that's hearts or diamonds, or a face card, a jack, queen, or king? So if we want the probability of drawing a red or a face card, all right, so that's going to be the probability of drawing a red card plus the probability of drawing a face card minus the probability that we have a red face card. All right, so the probability of drawing a red card, well, half the deck is red, half the deck is black, so we'll say that is 1/2. The probability of drawing a face card is there's only jacks, queens, or kings, but there's 4 different suits, so 3 face cards of each suit, 4 suits, that's 12 out of our 52 cards altogether. And then minus the probability that we have a red face card. Well, the red face cards are going to be Jack, Queen, King of hearts, Jack, Queen, King of diamonds. That's 6 cards total out of 52. So this is going to give us our answer. And if I can slide this down, this is just what we were talking about. 26 over 52 is the same as our 1/2. So I could have written this right here. 26 over 52. And then plus the 12 over 52 minus the 6 over 52 gives us 32 over 52, which is 8/13. All right, here's your next notes must do. A card is drawn from a deck of 52. Find the probability of drawing a king or a heart.
All right, so we're going to look at application here. Starting off with, starting off with 1,560 students that were surveyed. 840 of those students were seniors and 630 read a daily paper. The rest of the students were juniors. Only 215 of the paper readers were juniors. So what is the probability that a student was a senior or read a daily paper? So when we are doing problems like this, it's going to be easiest to set up a Venn diagram. And we're going to label as much information as we know. So since being a senior and reading the paper are inclusive events, which means that they have some overlap there, I'm going to start off with 2 different Venn diagrams. So I start off with one in blue and one in yellow. So what do we know in this case? We know that there are a total of 840 seniors. So the outside of this blue circle, this blue oval, is going to have to account for 800. Maybe we'll put it down here. There are 840 seniors that must add up to. In our other oval, we have our paper readers. And we know that there are a total of 630 paper readers. Now, of the paper readers, it said that 215 of them were juniors. Well, and you can already see we have this one labeled on here. I'm not going to put that 215 in any part of the blue oval because the blue is going to represent seniors. So I'm going to put that in the part that we have yellow only, so it's only in the part for paper readers.
So there's 215 in this area out here, correct?
Yeah. Now, in order to find some more information here, we're going to use what we've been given to find out where our other numbers go. So we're going to start off with here. We have a total of 630. We know that 215 of them have to go there. So what must go in this overlap portion? Well, 630 minus 215, that's going to give us 415. So that 415 must be the number now that goes in the middle here. That can then help us find out what goes in the rest of this portion for the seniors, what's going to fill in here. Well, there are a total of 840 seniors. If I take away what's in the overlap portion already, 415, and subtract that, that's going to give me 425. So this portion here must stand for 425 seniors who are not paper readers.
So step 2 now is to find the number in the overlapping region. We did that already. Step 3, find the probability that a senior and, find the probability that you pick a senior or you pick someone who reads the paper. So that's going to be the probability that you pick a senior plus the probability that the student that you pick reads the paper minus the probability of a senior who does read the paper. So in order to get that, we look at our Venn diagram. The probability that you pick a senior is going to be a total of 1560. So the probability would be 840 over 1560. All right, so that's the probability of 1,560, thank you. All right, plus the probability that the student reads the paper, and we know that there's 630 paper readers out of the 1,560 students, and minus the probability that there's a senior who does read the paper. That's 415 because that's our overlap area here. So that's minus 415 over the 1560. And when we work this out, we get 1055 over 1560, which is approximately 0.676. So the probability that the student we selected was a senior or read the daily paper was about 67.6%.
Now we want to recall back from lesson 11.2. I don't think that number's quite right, but that's okay. But that the complement of an event, maybe 7.2, that sounds better. The complement of event with probability P, all outcomes that are not in the event. So a complement is like kind of the opposite of what we're looking at. So what didn't happen? In order to find that probability, we're going to take 1 minus P. So you can use the complement to find the probability of a compound event. So again, this is if I told you the probability of rolling a 2 was 1/6, and I wanted to know what's the probability of not rolling a 2, you would take 1 minus 1/6. So take away the probability for the thing that you know. So we're going to use that idea here in order to answer this question. So we have each of 6 students randomly chooses a butterfly from a list of 8 types. What is the probability that at least 2 students choose the same butterfly? Well, in order to have the probability that at least 2 students are going to choose the same, I'm going to instead use the complement. And I'm going to say, okay, the probability would be 1, and I'm going to subtract from that any probability where they all choose different. So every student would have a different butterfly, because that's something that we can calculate a little bit easier in order for us to find what the probability of what I'm actually looking for. So we need to think about how could all the students choose a different butterfly? Well, there's 6 students, and they each have 8 choices. So my total number here is if each of those students had 8 different options. I mean, we're going to click on this, and then we're going to cover up part of this as we talk through it. So we have that we're going to talk about the total number of ways they can all choose, and then on top, only the ones that they could choose different butterflies. Well, we know that since there are 8 choices for each of them, every student, so my 6 students here all had 8 choices. So that multiplies to my total here as 262,144. That's all the different options they have. If I want them to all choose different, well then that's going to be something where the order matters. I don't want to have any overlap, and they're each getting assigned to each student. So order matters. I'll use a permutation. So my permutation here would become 8 times 7 times 6 times 5 times 4 times 3, or 20,160 different ways. So that gives us a probability of about 0.0769.
That's the probability that each student chooses different butterflies and no overlap, no repeats.
No repeats. So if I now want to find, okay, well, what's the probability that they all, at least 2 of them choose the same? Well, I'm going to take 1 minus that probability we just found. So that would tell us that we have 1 minus that probability we just got from this part here, that probability of what we actually were looking for, that at least 2 choose the same, is about 0.9231. Okay, so that's about 92.31%.
Okay, and that's it for this lesson. Make sure you've taken good notes and done the notes must do's, and we'll see you next time.